Hello friends, I am Prashant V Dhanshetti, Assistant Professor, Department of Civil Engineering from Walchand Institute of Technology, Solapur. Today I am here to explain about the numerical on moment distribution method. At the end of this session, the students will able to understand the procedure for analysis of indeterminate beams using moment distribution method. They will be able to analyze a continuous beam and draw the bending moment diagram. The moment distribution method is an iterative structural analysis technique used to solve statically indeterminate beams and frame. Now, as we all know that structure is generally classified in two categories as determinate and indeterminate structure or redundant structure. Determinate structures are analyzed just by the use of basic equilibrium equations. Redundant or indeterminate structures are not capable of being analyzed by mere use of basic equilibrium equation. Now, these are the steps that are to be taken to analyze a continuous beam by moment distribution method. So, assume all ends are fixed, find the fixed end moments developed for each span of the beam. Calculate distribution factors for all members meeting at the joint, balancing a joint by distributing balancing moment. The balancing moment is to be distributed with the negative value at the joint to the various members meeting at the joint proportional to their distribution factor. This exercise should be carried out for all the joints. Carry over half the distribution moment to the far end of the member. Repeat step 3 and 4 till the distributed moments are negligible. Sum all the moments at a particular end of the member to get final moments. Now, here you can see a continuous beam is there with a fixed end having a different moment of inertia. So, you can see span AB is having 1.5 I, span BC is having I and span CD is having 2 I. So, first step is to consider all the spans as fixed and we have to find the fixed end moments. So, if a beam is having a point load at its center, the fixed end moments at A, that is MAB, will be equals to PL by 8 and MBA is equals to also PL by 8. But here the anti-clockwise moment is having negative sign, whereas clockwise moment should be given positive sign. So, coming to our problem, the first span AB, it is having an eccentric load. So, this second case will be considered to find out the fixed end moment. MAB is equals to 60 into 4 into 2 square upon 6 square. So, it is 26.67. As it is anti-clockwise, we have to treat it as negative. Whereas MBA, so this moment will be, that is 53.33 kilonewton meter, it is considered as positive. So, now span BC, it is having a UDL throughout its length. So, minus MBC is equals to plus MCB, that is WL square by 12, that is 15 kilonewton meter. And again here CD span is having a point load at the center. So, minus MCD is equals to plus MDC is equals to PL upon 8, that is 30 kilonewton meter. So, here is a distribution factor table. So, we have to consider a joint B. So, the joint B is having members BA and BC. So, here this joint is having BA member and BC member. So, the stiffness of the member, as the far end is considered as fixed, for continuous also it is considered as fixed, and if it is fixed it is also considered as fixed. So, the stiffness is 4 EI upon L. So, here I of this span is 1.5 times I. So 4 EI upon L will give you EI. For span BC, again this is a continuous, so it is considered as fixed. So it is again 4 EI upon L. So here I is equals to I. So here 4 EI upon L, that will become 1.33 EI. So the addition of the stiffness at the joint will be 2.33 EI. So the distribution factor for BA member will be the stiffness of member BA divided by total stiffness, that is EI upon 2.33 EI, that comes to 0.429. Whereas the distribution for BC member will be the stiffness of that member divided by total stiffness, that is 0.571. So here now you consider the joint C. So here the members will be CB and CD. So far end is again fixed. So you will be having this as 4 EI upon L. Here also far end is fixed, it is 4 EI upon L. Repeating the same procedure, we will get the distribution factor for CB member is 0.571 and for CD member is 0.429. Now systematically arranging the moment distribution table. So these are the joints, that is A joint, then B joint. B joint is having member BA and BC, whereas again C joint is having CB member and CD member, and this is joint D. So the distribution factor is given for BA member it is 0.429, BC member 0.571, for CB member it is 0.571 and for CD member it is 0.429. So applying the fixed end moments calculated earlier, we have to balance this moment. So addition of this 53.33 minus 15, so the unbalanced moment is 38.33. So multiplying with this distribution factor and giving the opposite sign. So here that is 38.33 into 0.429 will give you 16.44, giving the negative sign here, and again that unbalanced moment multiplying with this 0.571 moment distribution factor, so that comes to 21.89 and giving it opposite sign. So this is the balancing moment. Similarly, the balancing moment is done at joint C. Now this balancing moment has to be carried over to the farther end, half of the moment. So half of this moment will be carried over to the fixed end, far end fixed, that is 8.22 at joint A, and further this 21.89 half this is transferred to this joint C, that is minus 10.95, whereas half of this 8.57 is transferred to this joint B, that is 4.29. Again half of this 6.43 is transferred to D, as it is a carryover moment. The same procedure again here, this is the unbalanced moment, that is 4.29. Again this balanced moment is distributed according to the distribution factor, that is 4.29 into 0.429, you will get this value minus 1.84. Again 4.29 into 0.571, you will get minus 2.45. Again here this is unbalanced moment, minus 10.95, multiplying with 0.571 and giving opposite sign, you will get 6.25. Again this multiplied with this distribution factor and with opposite sign it is 4.7. Again this carryover moment is done for the far end fixed. So like this we have to distribute the moment till we get a negligible balancing moment. After that we have to take a summation of all this moment, that is coming as 36.56 at joint A, then 33.45 at joint B, 17.91 at joint C, and 36.04 at D. Now, a free moment diagram for AB is a triangle with the maximum ordinate under the load. So, this will be considering the simple support, that is WAB by L, that is giving 80 kilonewton meter, and for this the free bending moment is WL square by 8, that is 22.5, whereas for this span CD it is WL by 4, that is 60 kilonewton meter. Now, to draw the bending moment diagram for each joint, so we have to consider the fixed end moments from the moment distribution table. So, the fixed end moment at A is 33.56, at B it is 33.45, at C it is 17.91, at D is 36.04. So, we have to join all this, that is having the negative moment. The positive moment of span AB is triangular, that is 80 kilonewton meter. Then for span BC, the bending moment, free bending moment is the parabolic curve, that is having 22.5 kilonewton meter, whereas for span CD it is 60 kilonewton meter. So, this is the bending moment diagram for a continuous beam. So, these are the references. Thank you very much for watching my video.